It's 7 p.m. o'clock Central European Summer Time. Good evening, good morning, and good afternoon to everyone. This is Gennardana from Legnano near Milan, Italy, and I'm so happy to be here to moderate this webinar. I'm always happy when we in USOMI talk about neuroimaging here. Prior to start, many thanks to Bracco for supporting us. Now it's time to introduce my co-moderator. The co-moderator today is Pınar Yılmaz. Pınar Yılmaz, beyond her today's role as my partner in crime, is a resident in radiology at the Erasmus Medical Center, and she is currently doing a research fellowship at the JPK Stroke Center in Boston. Furthermore, she is also a USOMI Young Club committee member. Pınar, the stage is yours.
Thank you, Gennaro, for the kind introduction. I'm glad to introduce a former colleague and a friend of mine, Dr. Florian Dubost. He's a postdoctoral researcher in biomedical data science at Stanford University in California and has 6 years of experience in machine learning. He holds a PhD in medical computer vision and reached top rankings in international deep learning competitions. He will enlighten us on the weakly supervised object detection with 2D and 3D regression neural networks. Those networks can compute attention maps to reveal the location of detected lesions, and we will get to see some examples of how this method works. Dear attendees, if you have any questions, you can write them in the Q&A box, and later at the end of the lecture, we will discuss all of them. Please also note that this lecture will be recorded and will be available on YouTube later. Florian, the floor is yours. Please unmute yourself, Florian.
Sorry. Thank you very much for the introduction, and thank you very much for having me today. I'm very happy to present, and I'm happy to answer all of the questions you will have, guys, at the end. So, yeah, I changed a bit the title of the presentation. So I'm going to speak about weakly supervised object detection and its application to neuroimaging, especially focus on brain MRI and one type of brain lesion / vascular change. And most of the results you will see in this presentation, they are actually published in this paper below. And that's work I did during my PhD when I was still at Erasmus Medical Center in the Netherlands, in Rotterdam. So that's what I was speaking about. Most of the presentation will focus on the quantification of enlarged perivascular spaces. And so what is it? In your brain, there are little blood vessels, and there is a space around this blood vessel, like on this figure here. That's called the perivascular space. It's filled with cerebrospinal or interstitial fluid. And for multiple reasons can become enlarged. And that's what we're trying to detect and quantify, these enlarged perivascular spaces. In the middle, you have the 3D reconstruction of one of the hemispheres with the perivascular spaces highlighted in blue, like segmentations. And on the right, there is an image with where you can see them as hyper-intense little tubular structure on T2 MRI. So why do we want to quantify enlarged perivascular spaces? Well, they are thought to be an emerging marker of small vessel disease, especially they have been shown to be related to stroke or vascular dementia or multiple sclerosis. And it's very difficult to quantify them manually because it's expert dependent and because there can be a lot of them, so it's very time consuming. There are some automated methods that exist, and those they are semi-automated, or they require a lot of parameter tuning, or they only work for some brain regions, but not everywhere in the brain, or not most of the relevant regions. And a lot of methods trigger a lot of false positives. So from the methodological aspect, I'm going to show some application and method development of weekly supervised learning. So weekly supervised learning is when you try to use labels that either are not sometimes incorrect or sometimes don't represent your data well or don't represent what you aim to do correctly. And that's very often the case in medical data sets where you don't have voxel-wise annotations. For example, like in the ideal case, you would have this clinician who do for each voxel what it is, and then you just feed that to your AI algorithm to be able to train it. But in medical data sets, if you have that, it won't be for a lot of images because it's too time consuming. And then I'll also give some insights about neural network interpretability. So, understanding what happens in the black box. So there are key changes with quantifying enlarged perivascular spaces, and so they are first small with respect to the image resolution. So like the small ones, they are just a few voxel wides. There can be many perivascular spaces in a given brain region, for example, more than 50. Their afferents differ depending on the brain region. So the perivascular spaces in the basal ganglia, they won't look similar as those as in the centrum semioval, for example. They also differ depending on the MRI modality and protocol. They can have there can be multiple other objects on the MRI that look similar. For example, white matter propensity lacunes, and that can mislead the automatic detection of enlarged perivascular spaces. Also, sometimes actually the manual identification. And now I said earlier, perivascular spaces, we just want to quantify those that are enlarged because it's the sign of underlying, it can be the sign of underlying cerebrovascular diseases. But it's not as simple. It's not like it's enlarged or not enlarged. The enlargement is something that is progressive. And that's one of the key challenges with perivascular spaces, that sometimes you will see some, but you won't know if you should quantify them because you don't know if you can really say that they are enlarged. So that's one, I think, of the core problems in quantifying enlarged perivascular spaces. And what I mentioned, that we don't have voxel-wise label to optimize our network. We only have image level visual scores that indicate the severity of enlarged perivascular space burden. So now a bit of background on neural network interpretability and computing network attention. So if you look at the images on the left, there are some mushrooms, and we give that to the neural network, and then the neural network predicts what object it's seeing in the image. So it would predict mushroom in that case, so that's correct. And then we can look at what region of the image the network used to do the prediction. And that's what you have here, the heat map. So you can see that there are these like red areas that overlay the mushroom. So that's correct. You see that here there's a small mushroom that is not detected by the network. And similar situation, the image on the right, like this one, the bigger mushroom is well detected, but the smaller one is not as clear. The type of methods to do that, they so I won't go too much in the details, but basically there's a layer at the end that's so a neural network is like a series of image filters. You can like that is which parameters are optimized with training examples basically. And you can see there is this layer here that is called global pooling that maps each of the feature maps. So that correspond each to a different image filter from a 2D image to a single scalar value. And then they are all aggregated into one single output, and that will be the prediction of the network. So like, for example, in the image of the right, is it a mushroom, yes or no? And this would be a probability, pseudo probability between 0 and 1. So if it's higher than 0.5, you'll say, yes, it's a mushroom. Otherwise, it's not a mushroom. That's what you do during training. So you just need to know whether there is a mushroom or not in the image, right? And then during inference, during testing, like when you finished optimizing your network, you just remove this global pooling layer. And instead of being projected to single scalar values, the images, they will just be, you take the same weights for the linear combination, W1, W2, Wn, and you do linear combination of these feature maps. And then you don't have a single scalar value anymore. It's just a feature map that is the same size of the F1, F2, the last feature maps of your network. And then you can, that's how you create the image on the left. So you can see what the network is looking at to do the predictions. So that's the method that's called CAM for class activation maps. It was proposed in 2017. There are other methods, for example, GradCam, that are variants of this, use the same principle, but they compute the weights differently. And then there's another method I'm going to show some results for, but I won't detail it here. So there's another group of methods that's gradient method. And instead of using the attention maps, the feature maps of the network, as I just explained, they compute the derivative of the output with respect to the input. So the output, it would be the logit, like how much the network thinks the image is a mushroom, and the input is the input image. So you can have for each value, each voxel pixel in the input image, how much it contributed to the output that is given by the network. So you can see, it's another way to see what part of the image contributed. Problem with that is that if you do it like straight like that out of the box, there are some interference patterns that create a lot of false positives. And there's been a paper in 2015 that proposed to correct that, but by changing or the information is backpropagated through ReLU activations. So there are, for both methods, there are a few problems. The first problem for the classification map methods is that if you look at this example here with the mushrooms, you see that if you want to delineate the mushroom, it doesn't work that well, right? It just like creates a big blob in the middle, but you won't be able to, like use this information to nicely delineate it. And the small ones, they are also kind of missed, And this is because we use the last feature maps of the network, which are usually downsampled by several factors in comparison to the original image resolution. So that's one of the first problems. The attention map, the resolution is too low. The second problem, or the problem I would say with gradient methods, is that they are biased towards silencing. They will focus on the region of the image that are silent, independently on whether they actually are meaningful to the target object. For example, here you see for corn, like it identifies the eyes of the person, the contour of their neck and arm, while this doesn't really have anything to do with corn. Same here, like it identifies the border of the box, has nothing to do with the dog. So to try to fix the first problem, there is this this network that is very popular in medical image analysis. It was proposed in 2015, and it's for segmentation. So it's this U-shaped network which does downsampling. So as I was saying, downsampling of attention map, but then to be able to output the images at full input resolution, it has this upsampling path, and then it combines everything with some connection in the middle. But yeah, that's basically the network of choice to do any kind of medical image segmentation. Now there are some new works with network transformer networks. So this maybe is starting to change a bit, but I think this is still the most popular. So the problem with this is that you need to have, at the end of your network here, you need to have a full voxel-wise annotation as labels to be able to compute your loss. You need to compute every voxel in your prediction to every voxel in some sort of ground truth. And we don't have that, right? We just have some image level labels, so we cannot use that as it is. What we can do, though, is to combine this network architecture that outputs images at the full resolution with the types of method that I showed earlier that compute this attention by adding global pooling at the end of the network. So that's exactly what we do. We just compute both methods so that eventually during testing, it still outputs a scalar value because of the global pooling layer at the end of the network. And during testing, during inference, we just remove this layer and then compute attention map at the resolution of the input image. The second problem is that, I told you, is there a mushroom in the image? Yes, no. Is there a dog in the image? Yes, no. Is there a corn in the image? Yes, no. That's what people typically do in computer vision, is that they have a classification network. That's one of the most popular tasks. And most of these methods of visualizing attention, they were developed for classification networks. But our scenario is a bit different. Most of the time, like almost always, we can see some pervascular spaces in the image. So the question is not, is there pervascular spaces? Yes, no. The only label is that we have is the number of objects, so the number of enlarged pervascular spaces. We don't know what they look like, the enlarged pervascular spaces, and we want to detect all instances of pervascular spaces. That's the most important. You saw in the example I gave above, there are some that were missed. That's not what we want. We want to really be able to, we don't care really if it's there or not. What we want to do is quantify them and detect them, find all of them. So what you can do to do that is, instead of framing a problem as a classification with binary cross entropy loss or softmax, you can use an MSE loss function, so a mean squared error, where you output a number at the end of your network. You don't do any activation, so it's still like a real number, and you compare that with the number of pervascular spaces that there are in your images, or like the severity score. And that actually helps to do object detection in general if you have image-wise label. So this here, it's a little example so that you understand little toy data set where we're trying to detect all the digits 4. Okay, and in the image on the top, we created a grid like this artificially. On the image on the top, there is no digit 4 in this image. You can look. In the image on the bottom, there are 7 occurrences. So 1, 2, 3, 4, 5, 6, 7. So we just give that to the network and we optimize it with like 0 in the first case or 7 in the second case, right? Just as access to the number of objects to be detected. And then we compare an approach that would be classification. So it just says whether there are objects or not, and an approach that does regression, well, using this MSE loss function I was mentioning earlier. And it's actually like the object detection works better when you use this regression type of losses. So this is just a qualitative example, but here there are some quantitative results computing the an equivalent of the ROC curve, basically. And where you see all networks that are blue, light blue, it's results that are light blue that corresponds to networks that were trained with regression objective, regression loss function. And the purple one, it's classification loss function. Each plot is for the detection of a different digit. So here is detection of digit 0, here is detection of digit 1, and so on. Each column, it corresponds to a different type of attention computation methods, you know, the different method I showed you above. And on the y-axis is this like area under the curve kind of metric. So the higher, the better. And you see that basically for almost all cases, with the exception of here and digit 7, it's always better to use the regression loss to do object detection using image-wise labels. So, okay, that's our methodology. Now we are going to apply this to enlarged pervascular spaces quantification and detection. We have a data set with T2 weighted MRI scans. We have 2,202 participants with each one scan, do a cross-sectional study. Participants are in between 60 and 90 years old. This is with a 1.5 Tesla scanner, 0.5 by 0.5 by 0.8 cubic millimeter voxel resolution. So that's actually pretty good. We use 1,202 scans for training, and the rest it's left out for independent evaluation. And so for training, we have these visual scores I'm mentioning about, earlier that indicate the number of perivascular spaces in the target region. So for example, if I have the basal ganglia, it will tell me, okay, in this person, for this participant in the basal ganglia, there are 5 enlarged perivascular spaces. And then it will tell me, so that then I will use that to train a network. Then I have other labels, each for a different region. In total, I'm going to look at 4 different regions: the midbrain, hippocampi, basal ganglia, and enlarged and centrum semioval. So that's what I use for training. For evaluation, we actually ask some radiologists to go through the scan and in like multiple slices, do some dot annotations at the center of enlarged perivascular spaces so that we can evaluate our detection methods. But we don't use these labels for training. This is only used for evaluation. So architecture, I won't go into detail. If you have questions, I can show you. But it's basically a variant of what I explained earlier, this sort of UNet network and with this global pooling at the end. We use the MSC loss function. The optimizer is ADA delta. And we do some data augmentation during training, little rotation, translation, flipping the images to add some regularization to the network. These are qualitative results for the hippocampi with different methods. The proposed method is GPUNet. And then you can see that, so for example, so this is an earlier method, you can forget about it. This one is a variant of CAM. I won't go too much in the details with that one. Usually it has the problem that it's detecting 2 large regions again. This is GradCam. It's actually one of the good methods. In this case, it doesn't work very well because it focuses on, you see like here, for example, the sides of the hippocampi. So this is not perivascular spaces. So you're probably not used to see that if you're radiologist, because what I did is that I used some free surfer parcellation of the brain in different regions. And then I created some sort of smooth mask and I applied that to the image so that I can only get the part of the image that are relevant, for the task. The idea behind this is that I give some prior knowledge to the network in the sense that, okay, you only need to look at this region, don't look at perivascular spaces elsewhere. So this is easier to optimize the networks. And that's what I'm showing here, the masked brain region. So this is part of the hippocampi, and then you would scroll up and down to see it as a 3D volume. So this was given as a 3D volume. And so you see that here it focuses on the side. This is just like cerebrospinal fluid. It has nothing to do with really like perivascular space. And that's what the network is focusing on. Here, there is a perivascular space that is not detected. Here there are two, but they are not detected very well. And also detect like focuses on basically hyperintense region in the image, independently or not, whether it's perivascular space or not. GRAD, you see, it's not very clearly seeable here, but it also misses, like the relevant perivascular spaces. Not very good result for backprop here. This is if you would use the intensity directly, to quantify perivascular spaces. Maybe you want to trace, because perivascular spaces they appear as hyperintense on the image. So you could say, okay, I want to do a threshold on the intensities, and that's going to give me a pretty good estimate of the load of enlarged perivascular spaces, provided I have segmented my region of interest. Well, yeah, it doesn't work that well again because of this, little hyperintense regions that are not perivascular spaces. And the GPU net, on the contrary, you can get a pretty decent, it still detects only one perivascular space, but it's actually pretty difficult to see both. Yeah, so this is just qualitative result on hippocampi. Now I'm moving to a more interesting, more thorough images of the centrum semioval. So this region is much larger, and there are consequently more perivascular spaces visible. You see that the method, they sort of agree. So here, again, these are two large detections. You cannot really identify the different perivascular spaces. You see that here in this area, the GPU net, it's a bit better, at detecting different perivascular spaces than GrabCam. The detections are a bit smaller with respect to what I was saying with the image resolution, or the resolution of the attention maps. Here, GRAD and gated backprop. So you see there are a bit fewer detection for gated backprop, which is in line with what I told you earlier. There is less false positive detections, and if you want to use the intensities directly on this image, it doesn't work at all. It's even worse than the hippocampi. Okay, so you see, like here, the one I circled is they actually correspond to dot annotations from the radiologist to indicate perivascular spaces. And you notice that a lot of methods, they detect perivascular spaces in this upper region here. But that's not been indicated by the writer. And those little hyperintense structures, yeah, they actually are perivascular spaces, but they were just not annotated by the writer for whatever reason. Like maybe they just missed them, maybe they just thought they don't have, their intensity is too low. That's what I was explaining earlier about the enlargement of perivascular spaces being a continuum. So eventually you have to make a choice as a writer on basically how light the perivascular space is on T2, because you could think as the color being a marker of its enlargement. So the lighter, the more enlarged; the grayer, the less enlarged. And yeah, so the writer didn't annotate them, but all methods focus on them. So this poses some problem, of course, in the evaluation. I'm going to come back on that afterwards. So here we show some results for the region I showed, the hippocampi and the centrum semioval. I also, as I mentioned earlier, we also did it for the basal ganglia and the midbrain. Just didn't put the result in this presentation, but you can check the paper. Everything is thoroughly reported there. So you see that this is what I explained earlier, some sort of, the FRC curve It's a variant of the RC curve. So RC curve normally is like the same y-axis, but on the x-axis, instead of being the number of false positive and average per image, you would like rescale that by the total number of negatives. The problem is that, you know, what's the total number of negatives? The total number of voxels in the image. Then, you know, there are a lot of voxels in the image that, you know, it's not relevant to include that in the plot. And if you do that, it will just squeeze all your ROC curve to the left. So it would look very great. You know, you would have like very good AUCs, but it's not nice to compare differences between methods. So that's why we use the FROC curve here. And then we just do an integration under the curve to compute this equivalent of the area under the curve called FAUC. That's why when you see, for example, here, so these are the curves, these are the FAUC that corresponds to this curve with confidence intervals computed with bootstrapping. So if you see, for example, this, you know, if you think in terms of AUC and RC, you think, oh, 36 is weird, it's worse than just average. But no, because, you know, that's not, it's not integrated the same. So this is actually good. Like, for example, like, let's say, for example, this one, GPU net 50, you think, okay, it's the same as average. But if you look at the curve, it's the blue curve here, and it's very close to these little triangles that indicate the intra-rater agreement. So the intra-rater, the rater did it twice, did the dots twice on the same images with a few weeks of interval. And then we compute their score. So we set one of the time point as the ground truth, and then the other one as the detection, and vice versa. That's why you have two little triangles. But yeah, so you see it actually comes very close to the intra-rater agreement. So we wouldn't expect to significantly overcome that, right? Because that's the maximum level of performance we can have to quantify endless pervascular spaces with those scans, or at least it's an estimate of it. And yeah, so you see that the intensity methods in green is just very poor, as I was explaining earlier. One of the top methods is the proposed method, and also in those cases, GradCam. In the basal ganglia and basal ganglia and midbrain, I've not shown this result here, but the method gated backprop actually is pretty good too. This one. So on the plot, it is the brown line. Here you see that's actually also, you know, pretty similar to the other methods. So that's like take back from this, like for this task, the best method, I think they are GradCam, gated backprop, and the proposed method, GPUNet. Okay, so let's just come back quickly on the, you know, these cases where there was disagreement between the rater dots and the detection of the method. So we asked actually Pinar, who just introduced the talk earlier, to go over cases of disagreement where the method outputs and the annotation of the first rater were different. We asked her to go through it. We designed little software to do that easily. And ask her, you know, what this object was, you know. So whether it was a pervascular space or whether it was other types of objects. We actually made some categorization of white matter impensities, lacunes, just like CSF, you know. And we found that in the hippocampi, all like cases of disagreement that were identified by the method GPUNet. We just did this analysis with GPUNet. 63%, which is 20, so this was on a smaller set, so just 20 objects, they are actually Perescott spaces. So most of the cases of disagreement, they actually correspond to Perescott spaces. Whereas for the rater, that was only 34%. So actually in the hippocampite, the method was a bit better, you could say. In the centrum semi-oval, the percentage, they are similar, but the rater identified more Perescott spaces overall, probably because they had like, you know, a lower detection threshold, lower you know, threshold of enlargement, this image intensity. So here there are some examples on the right, with the blue being the detection of the method, the automated method, GPUNet, and blue being the detection of the rater. So you see that there are quite a few cases of disagreement. But again, you know, there are quite a few cases of disagreement, but it's not that different from the intra-rater disagreement. And with this analysis, we show that the quantification of enlarged Perescott spaces, the detection of enlarged Perescott spaces is similar with the automated methods as it is with the manual annotations. Okay, so this is a bit, this is a little extension. I'm not going to show quantitative results here. This is just something I did at the end. We didn't completely go through it, but we could, I focused a lot in this talk on detection, right? Just finding where they are. But what's interesting also with Perescott spaces, it could be interesting to maybe look at association with different cerebral vascular diseases or determinants. It would be interesting to look at not just where they are, but also maybe their shape, their size, you know, and we cannot do that just with the detection. We need to do a segmentation, but we cannot do a segmentation because we don't have voxel-wise information. As I was explaining earlier, don't have voxel-wise ground truth labels. So that's, you know, like the next challenge, I would say. There are some people who are starting to do that actually more and more, doing like some like manual ground truth in a few scans, but you won't have like data set of 1,000 images annotated with you know, voxel-wise. So what we're trying to do is modify a bit the method so that in addition to doing the detection, it can also do segmentation, only being optimized with the voxel, with the image-wise label. So we're just going to say, for example, in these images, there are 26 Perescott space, and the network can do this segmentation as you see on the right, just from the number of voxel, the number of Perescott spaces as ground truth. And yeah, so the idea behind this is basically to replace the last activation of the network with a ReLU activation to be able to rescale the image intensities of the attention map between 0 and 1 so that you can easily segment at 0.5. Otherwise, it's unbounded and it's very difficult, you know, to consistently choose an appropriate threshold without, you know, overfitting on your data set. So that's what we did. There are some tricks with this because it's difficult to optimize just with a ReLU. So we actually optimize it in multiple steps where we keep a very large chunk of the network frozen. So we don't we optimize different parts of the network in different steps to make it simple. Yeah, but it's possible. But it's possible. We show that it's possible. So as conclusion, we show that you can combine UNet and classification maps to create more precise localization and potentially segmentation. We show that if you use regression objective, you can improve the weakly supervised detection of multiple objects in comparison to just using a classification objective. We showed that the detection of enlarged perivascular spaces was as good as that of manual annotations of experts. One of the limitations of the work is that we use just one rater for the number of perivascular spaces, one rater for the annotation. So it could be better to have multiple raters and maybe look at some consensus of ratings. Yeah, that's something we didn't do in the study. We prefer to have more images and less rater than the opposite. There's a challenge also with 7 Tesla images where you actually see the perivascular spaces much better, but you also see many more perivascular spaces. And then this question of, you know, the continuum of the enlargement, what perivascular spaces should I count as enlarged, which shouldn't I count as enlarged? It's becoming even more prominent. So it see perivascular spaces, but it brings new challenges. And from the weakly supervised detection approach, here I showed a lot of cases where, you know, with perivascular spaces, hyper-intense image of the image, they are informative. But what about cases where that's not the case? You know, that's where you just have to detect an object that has different image intensities. That's not as clear what happens there. And that's all for the presentation. Thank you very much for listening. If you want to have more details, also about just quantification of perivascular spaces, without the detection, for example, or how well does it work if you want to use it to look at association with determinant or outcomes. There are a lot more details in the book, my book that I published for my thesis. Yeah, you can, that's the title. And thank you very much for your attention. I'm happy to answer any of your questions.
Thank you so much, Florian, for your presentation. Now it's time for Pnar to read some questions from the audience.
Yes, thank you, Florian. There's a question by Tuba Akunje. She asks if one can use your model to discriminate perivascular spaces from lacunar infarcts, or have you tried it in your study?
Yeah, so we did that. We looked into that. Actually, Pnar looked into that. We didn't see any problems in that. Like there was so there are several parts of the answer. First of all, we do that in a population study. So then, like infarcts are not very prevalent. So we didn't have a lot of data to do that. On the data that we have, we didn't identify any problems. One of the important or interesting aspect in that is that, you know, when you want to look at infarcts, you may also want to look at the flare sequence, for example. Yeah, I only spoke about the T2 sequence. As a radiologist, you would want to look at both. And actually, our method, just looking at the T2, they didn't have problems, you know, with quantifying infarcts, because just the you know, the structure, the 3D structure, there is a strong prior there. So depending on the shape of the lesion, you can, you know, see whether it's perivascular spaces only on T2. When perivascular spaces are very close to each other, you can have you know, this sort of merge on the image, and it becomes more difficult to analyze their shape, and that's why you can start confusing them with infarcts. So there are some cases like this where it has been difficult, but the method still detect perivascular spaces correctly in those cases. Yeah, I think to really evaluate this more extensively, would need to do it in a study where you know, a participant who have cerebral small vessel disease. Yeah.
Yes, in a more diseased population, you could, yeah, you also encounter more of these lesions, so it would be nicer with your method to see if they separate or detect the perivascular space correctly without identifying lacunar infarcts instead.
Exactly.
Thank you, Florian. I also have a question. We've discussed this multiple times at the department as well, and also with other colleagues. What your opinion on people can be very skeptical on like attention maps and heat maps because it's also somehow the algorithm that you train to focus on them. What can you say about that? I mean, I think for to see what's in the black box, I think these kind of methods are necessary. Also to somehow improve your algorithm, but also to show what it does.
So what's the question exactly?
So what the people can be skeptical about those methods. Like, how do you look at that?
About the attention maps methods or about neural networks in general?
No, attention maps specifically.
Okay. Okay, so
I know that some people don't really believe in them because they think they're also trained to, focus on them.
Yeah. So okay. So first of all, like the attention map, that's the point that it's not trained. The network is not trained to specifically focus on some region of the image because you have an image-wise label. The network is just trying to reproduce this image-wise label with any information they can find in the image. So we don't force it actually to look at some region of the image. So I'm not sure that's really the problem. I think what is more interesting though is that I showed some example of attention map earlier, and depending on what method you use to compute them, you will have different results, right? For the same network. For the same network, if you use, for example, grad or get backprop or gradcam or GPUNet, you will have different results, okay? And so that can be, like raise question, okay, what's the network? What is the network really looking at? So that's a good question. I don't have a very good answer for that. I would say that maybe what the network is looking at is, an aggregation of all these different attention map methods. I think it's, you can be skeptic about attention map methods, but as Painar started to mention, that's going in the good direction, I think, for neural network interpretability. It's better to have an attention map than not having it. Gives you a bit more understanding of what's happening, even if it might be a bit biased. And in this work, we use really the attention map methods for weakly supervised detection. So we don't claim, okay, when the network only looks at this, but we say, okay, we can use these methods and to do detection. So we can solve a detection problem, and we compare that quantitatively with manual annotations. So I think a lot of work who compute attention map, they actually don't compare that with some voxel-wise type of information. They usually do some more qualitative evaluation. That's because they don't have this voxel-wise information to compare with in most cases. So I think that's one of the interesting aspects of this work, that we provide the quantitative evaluation of attention maps.
Yeah. Thank you for your clear answer on that. And thank you again for being with us during this May webinar. And thank you all attendees. We would like to thank Bracco again for sponsoring us, and we hope to see you all during our next webinar in June. Have a great evening, everyone.
Thank you very much
to all. Thank you, Florian, and I hope to see all of you in the next webinar in June, and on the others for the next the rest of the year. Especially, I have sponsored the ESNR joint webinar we will see in the late of this year. So I will be so happy to share the partnership between ESNR and Eusomi. And as usual, from Eusomi, good evening good afternoon and good morning to everyone. I see you next time. Bye-bye.
Bye.
Bye-bye. Thank you very much.